So I don't really know how to segue into the start of this video, so I'm just gonna start talking and hope I find my way. Although, before I get really in depth in talking about electron orbitals, I want to talk about the history of atomic models, because I'm a big ol' nerd. So the first idea of atoms comes from ancient Greece and the word atomos, which means indivisible, which we know atoms aren't divisible now, but they just kind of thought that atoms were these little tiny things that made up everything. But the first actual model of the atom came from John Dalton and his solid sphere model. Behold, the atom. You know, honestly, I thought it would be more impressive. And Dalton's model is wildly incorrect, but he did recognize that atoms of individual elements are identical. He knew that gold atoms are going to be different from iron atoms, but one gold atom will be identical to another gold atom. The next sort of major breakthrough in atomic models came like 100 years after Dalton with the plum pudding model. I don't care if it's inaccurate, it's fucking delicious. This model is mainly noteworthy because it recognized that electrons are an actual thing that exists and are part of atoms, but it failed in that it didn't have a nucleus, which is not the best thing to forget. So surely now that we know electrons are a thing, the next atomic model is going to be great, right? Son of a bitch. Yes, this was Ernest Rutherford's atomic model, which he came up with after his famous gold foil experiment, at which he shot alpha particles at gold foil, and most of which passed right through the foil, but some reflected off at large angles, which would only be possible if the atom was mostly empty space. And so Rutherford proposed that there was a tiny nucleus at the center of each atom, which the electrons orbited around. But he didn't really explain why the electrons stayed in orbits. And now comes the model of the atom that most people who take a general chemistry course are probably familiar with, the Bohr model of the atom. And if I'm being completely honest, I find this model kind of boring. I'll show myself out. In Bohr's model, he explains that electrons stay in fixed energies around the nucleus, although what he didn't really account for is that over time, these electrons should theoretically collapse into the nucleus and destroy the atom. And now we get to Erwin Schrodinger. You know, the guy with the cat? Schrodinger had the quantum model of the atom, where he proposed that electrons didn't necessarily move around the nucleus in discrete orbits, but rather they existed in a cloud of electrons, and we had no idea where their position was because of the Heisenberg uncertainty principle, where you can either know where something is or how fast it's going, but not both. And in this model, orbitals became less orbits and more just clouds of probability. And this is where I'm gonna start getting into the weeds on electron orbitals. You see, to figure out where electrons sort of end up in these clouds, Schrodinger used what is now known as the Schrodinger Equation. And the Schrodinger Equation in its simplest form looks kind of like this. And I'm not gonna go too deep into the math because, let me double check something. Yeah, it's complicated. But with the Schrodinger Equation, this little part, this symbol psi, it represents the wave function of the electron. And those sort of determine the orbitals, because if you take it and you do some math with it, you can find the radial distribution function, and that sort of gives you the probability of where an electron of a certain orbital is likely to be, and that's how we get all the sort of shapes of orbitals. Because electron orbitals aren't perfectly spherical or circular or however you picture them. There are orbitals that are that way. Those are the s orbitals. They're very simple. They're a sphere. They're awesome. I love them. But we start getting more complicated with p orbitals, which have this sort of weird barbell bow tie shape to them. And there are 3 different p orbitals that exist in an atom. There's one along the x direction, one along the y direction, and one along the z direction. And how do we decide what direction is what direction? We just assign them and hope the math works out. And then you get d orbitals, which is kind of like 2 p orbitals overlapping, and they mainly exist in the transition metals, you know, that big chunk of the periodic table with like iron and cobalt and zinc and stuff. And d orbitals are interesting mainly with transition metal complexes, which are probably beyond the scope of this video, so I'm going to shut up about them. And then you get f orbitals, and no one really draws f orbitals, because f orbitals are the ones that exist, and there's like last two rows of the periodic table with all the radioactive stuff, so you tend not to deal with those quite too often. And all of those shapes come from solutions to the Schrodinger equation, which I think is really freaking cool. And it's probably important to note that those shapes come from the solutions to the Schrodinger equation for specifically a hydrogen atom. Because, like I said before, the Schrodinger equation is complicated and it can only be solved for a certain number of systems, namely a particle in a box, a harmonic oscillator, a rigid rotator, and a hydrogen atom. Anything beyond that, and you have to use approximation methods to actually solve it. And that's where you can start getting into computational chemistry and making computers do all the work for you, because the math is really fucking complicated and it would take forever, or it would be impossible to do it by hand. So before I wrap this video up, I want to talk about molecular orbitals, because they're rather interesting and they help us understand how atoms actually form bonds in compounds. Although it's probably important to mention phases of orbitals at this point, because orbitals have phases. You can have a positive or a negative phase. Like with an s orbital, it's either all positive or all negative, but with a p orbital, you usually have one lobe positive and one lobe negative. And that sort of forms the basis of molecular overlap, where you want things to be in phase for constructive overlap, because that will lead to a stronger bonding interaction, and you don't want destructive overlap because that will lead to an anti-bonding interaction. And the simplest thing to talk about with molecular orbitals, I'm just going to talk about hydrogen gas, because it's H2, it's very simple. The molecular orbitals are very easy to understand. You take the s orbital of one hydrogen atom, you combine it with the s orbital of another hydrogen atom, and you get a bonding orbital and an anti-bonding orbital, because that's just how quantum stuff works. That's pretty much all I have to say about electron orbitals at the moment, because I can get really into the weeds and get really technical about it, and this video would be an hour long, but no one would watch it. So I'm gonna leave it there. If you made it this far, all two of you, thanks for watching. I'm out of breath now.